Very nice. So I will be talking about a new global multi-source sea ice concentration composite, which is work that I've been doing with various colleagues that are listed here. And first, I want to talk a little bit about the motivation. So we wanted to make a sea ice concentration composite that contains the most accurate available information. But at the same time, we wanted to ensure that we have consistency. So a part of that means making sure that we don't introduce any trends in data from combining products. And then another requirement that we had for this data set was that we wanted daily global coverage from 1982 to 2024. And with that demand in mind, our primary input to this multi-source composite is sea ice concentration climate data records that are based on satellite passive microwave data, partly because we have long time series. They can penetrate through cloud cover and are independent of sunlight. And for that reason, we have global daily coverage, except for the pole hole. So some of the challenges that we encounter when we want to combine different data products is firstly, of course, that we have sensors that will eventually stop working, but also that we have better data that becomes available over time. And with new sensors comes also new characteristics, such as differences in resolution or footprint, but not only limited to that. There's also can also be with uncertainty or with the setup of the sensors that we have. And the figure that I have over here to the left, that's just an illustration of one of the things that we encounter that causes challenges when we are combining different passive microwave-based products. So this purple circle shows an example of what the resolution of the coarse resolution sensors that we will use have. So that's resolutions about in the like 70 kilometer scale. Whereas for newer sensors, such as the AMSA2 and AMSA-E, we have much higher resolution down to around 25 kilometers. And that comes with some challenges that we need to face when we are trying to combine these products so that we can actually use the best available information. With that said, I will go into the input data that we have used in this composite. So as I mentioned before, our primary input is sea ice concentration climate data records that are based on passive microwave data. And here we want to use this product, the OSI 458, whenever that's available. And that is because it's based on the AMSA-E and AMSA-2 sensors, so it's higher resolution data. As a second option, we want to use the SIGI high resolution sea ice concentration product. That is based on information from the same sensors as this OSI 450A, but there has been done some extra processing to include information from the higher frequency channels, which makes it contain better features. However, that's only available from 92, and therefore we use the OSI 450A climate data record whenever we don't have the others. Apart from that, we also include information from ice charts. In the Baltic Sea, we use the FMI, SMHI ice charts. That is a challenging region for passive microwave radiometers. And then apart from that, we also use ice charts from the US National Ice Center. And the reason for that is that these do not only contain sea ice concentration ice charts, they also contain additional information, such as what we are using here, which is that we can take the landfast ice information. So that's what's shown up here in orange as an example. However, these ice charts are available on around bi-weekly timescales, just to keep that in mind. We also use these ice charts for filtering, and the same goes for sea surface temperature products. We also use them for filtering, and I'll come back to why that is necessary when we are combining these products. So here we have the processing chain. We start out with regridding our data to a regular 0.05 times 0.05 lat long grid. And then we choose the most accurate available sea ice concentration data. And that's based on that time series I showed before with whatever data we have available for a specific time period. However, we also have some gaps in the sea ice concentration data where we don't have any available information. And then we do a linear weighting of the closest available sea ice concentration data. After we've done that, we add the sea ice concentration data from ice charts to the Baltic Sea. And then we apply filtering methods to ensure that we don't introduce any trends from this combination. After that, we extrapolate the data into coastal regions. And then we add the landfast ice, where we add landfast ice from the closest available ice chart. As a very last step, we do an adjustment for the pole hole for SIGI high resolution, and I can get back to that, but basically there's just been a more sophisticated interpolation in the pole hole for OC 450A, which we are using. And then we also apply a bias adjustment to the coarser resolution, sea ice concentration, climate data records. And I will also get back to why we need that even after the filtering. So why is it that we actually need to do filtering? That is what I want to show with this figure. So what we see over here on the left-hand side is reference images from Modis Aqua for the 28th of July 2017. And what we can see is that we have at least almost entirely ice-free conditions. This figure that you see up here, that's consistent with the orange box, and then the figure in the bottom, that's consistent with the gray box. What we then see for these three different primary input sources to our data set is that they disagree a lot about how much sea ice concentration that there are in these near coastal areas. And that is due to something known as land spillover, which is caused by the fact that the brightness temperature of land and the brightness temperature of ice measured by the radiometer tend to be in similar ranges, whereas the ocean is much colder. Therefore, with the coarser resolution sensors, we can have contamination from the land that then gives false ice. And there's already being done quite a few steps to adjust for this. But as we can see in the top pane, it's not completely removed this issue even after that. Therefore, we need to introduce some additional filters to ensure that we obtain something which is consistent along the three different products than what we've shown here in the bottom pane, where we now see that we have a much higher agreement between the three different products, and also that they agree with our reference images from Modis. So what kind of filters are we actually applying? I'm going to go through them quite briefly, but we have a filter where we look for near land grid cells with a sea ice concentration higher than 0. And then if we also have a nearby grid cell that has a sea ice concentration of 0, then we say, okay, this is probably falsely predicted ice. Our second filter uses the sea surface temperature information, and it says if we are near land, we have a sea ice concentration higher than 0, and the sea surface temperature value is above 3 degrees Celsius, then we also believe this is a falsely predicted ice. Then we have a global filter, which just says that if the sea surface temperature is above 8 degrees Celsius, then we don't believe that we have sea ice concentration higher than 0. Our fourth filter uses this information from the ice charts, where we say that if we have 2 consecutive sea ice charts that have a sea ice concentration of 0 for a near land grid cell, then we believe this needs to be water and not higher than 0 sea ice concentration. And then the last step we do is this biased adjustment, which is an inter-sensor bias adjustment that is applied to OC 450A and SIGI high resolution, where we use the OC 458 as the reference. So looking a bit more at the impact of these filters, we're going to be examining these heat maps. And what they show on the y-axis is the sea ice concentration, and on the x-axis is the sea surface temperature for the 3 different primary passive microwave input data sources. And what we can see is on the top pane that we have quite a big difference in the 3 figures. They do not look the same, although they are from the June 2007. And if we want it to be consistent, then they should also look very similar. However, we can see we have way more data points with these high sea surface temperature and intermediate sea ice concentrations in the coarser resolution-based sea ice concentration products than we see over here, where we have a higher resolution basis for the sea ice concentration product. After we have applied our filters, we see a much higher consistency between the 3 different data products, which is basically the goal that we wanted to obtain. Just a note that this line up here that comes from the inclusion of landfast ice, which can have higher temperatures. For the southern hemisphere, the picture looks a little bit different. And the main reason for that is, as we can see here, that we don't really have high sea surface temperatures in ice-covered regions. So all of our data is lying over here with the cold sea surface temperatures. And that also means that after we apply the filters, we don't really see any impact. So the filtered sea ice concentration looks almost as the unfiltered sea ice concentration in terms of consistency with sea surface temperature. So with all of these things in mind, then why do we still need to do the bias adjustment? And the reason for that I have attempted to illustrate in these figures. So what we see here is an example of when we would have higher than 15% sea ice concentration for OC 450A, whereas we would have a lower than 15% sea ice concentration for OC 458. So lower resolution sensor, higher resolution sensor. And we can see that we have a lot more data points along the ice edge, which we are not correcting with our other filters, where we have more than 15% ice concentration for OC 450A, signifying that we would also have a larger sea ice extent. And that will cause inconsistencies if we do not correct for this. And it's most likely caused by something known as ice spillover, which is due to a more smeared signal from the lower resolution sensors at the ice edge, which also then makes the edge appear further out in the water. So the solution that we do is that we adjust the OC 450A and CG high resolution by finding monthly mean differences in the sea ice concentration between the OC 450A and these 2 other products, both for Northern Hemisphere and Southern Hemisphere. And then we fit a function to the differences and subtract this from the coarser resolution-based sea ice concentration climate data records. So, in the end, what is actually the impact of the filtering on the sea ice extent? And sea ice extent, just to let you know, is for the area of sea ice concentration above 15% sea ice concentration. We can see for the Northern Hemisphere that the bias adjustment here is noted as final correction has quite a big impact. And otherwise, it's especially the ice charts that have an impact. We can also see that the bias adjustment is biggest for the period where we have the OC 450A and smaller for the CG high resolution period, indicating that something in the inclusion of the 90 gigahertz channel has made it more similar to OC 458. We can also see that we have very little sea ice extent impact for the AMSA 2 period, which is also what we would expect to see. For the Southern Hemisphere, we can see that really the only thing that makes an impact is this bias adjustment. And that is expected to be due to several reasons. Firstly, we expect less land spillover in the southern hemisphere because we don't have this complex land pattern around. Secondly, we could see that the sea surface temperatures were much colder, making the impact of our sea surface temperature filters very small. And thirdly, we don't have reliable ice charts for the southern hemisphere. Therefore, we are not using them for filtering. We're also not including landfast ice for the southern hemisphere. Yes, I'm gonna move on. So, what actually comes out of our data set? This shows the different variables that we have in the end in our data set. So we have the ice concentration that we've made, so that is filtered and extrapolated into coastal areas. Then we have what we call ice cons origin. That is just the data added, but without any filtering and extrapolation. Then we have the sea surface temperature information that we have used. We have a mask with ice, marginal ice zone, open water, and land. Then we have the ice source telling us where the data comes from. For instance, where do we have landfast ice from ice charts? Then we have a status flag telling about the amount of correction or filtering done to a grid cell. And then we have the source of the sea surface temperature information. So, the probably most interesting slide. This then shows a comparison of the sea ice extent between our data product for the whole period when compared to climate data records from OSI 450A and NSIDC. And there are two things that I want to highlight in these figures. And just to let you know, so we have Northern Hemisphere here, Southern Hemisphere here, September extent on the right-hand side, left-hand side, and March extent on the right-hand side. And what we see, firstly, is that we have a trend that falls within that of the two climate data records, which is very good, because that means that we have not introduced any trend to our data from the combination of products. And that goes for all of the four different examples shown here. Secondly, we can also see that the absolute value of our sea ice extent follows really, really closely the OSI 458, which is our reference. That's the highest resolution data that we have available. And that's also very good to see, because that means that we are somehow successfully replicating the trend of this data. If we did not apply any filtering, what we would have seen would have been a jump from the yellow line we see here and down to the blue line. So therefore, we are clearly doing something correct with this filtering and adjustment compared to if we had just patched the data sets together. So, a conclusion. We have combined some existing sea ice concentration data sets to provide the most accurate available sea ice information in the period of 1982 to 2024. And what we see is that we have a much higher consistency between the sea ice concentration input sources after we apply our filtering and adjustment. We also observe that we see similar trends in the DMI multi-source composite sea ice extent when we compare it to those from NSIDC and to OSI 450A climate data records. The last point just to note is that this data set is currently being used in the CARA2 production and also in the production of the global sea surface temperature within the C3S. For further development, we want to look into a more sophisticated bias adjustment between the OSI 450A and CG high resolution sea ice concentrations and the OSI 450A, so the quasi resolution and the higher resolution data. We also want to further examine how or if to adjust the southern hemisphere sea ice concentration data. What are the correct measures to use here? Because we could see that the filters currently used don't really have an impact, and maybe that's right, but we would like to examine that more. Lastly, we want to look into some IST sea ice concentration inconsistencies in the marginal ice zone that we have found when we were examining the sea surface temperature data within the C3S global SST product. And if I have time, I just want to show a quick teaser to that issue, and maybe some of you have some ideas as to how we can use this information best. So the challenge which we observe is that we have what we see here firstly is the sea surface temperature from the C3S global SST. And we have calculated some under ice sea surface temperatures. And then we have the temperatures here from observations just on the outside. But what we can see in this area here is that we have some areas where we have a very cold sea surface temperature, ice surface temperature, but a sea ice concentration of 0. So here we believe it to be open water from the ice data, but the temperatures indicate that this should be ice. And we would like to see, and this is the margin ice zone. It's known to be a super challenging zone. And we would like to see if we can somehow maybe use this information that we have from the SST, IST to adjust these areas, because it could indicate maybe that the marginal ice zone, we're actually removing too much ice in this area, or that it's not either us or in the production of the CDRs, because we can also see it in the AMSA2 data over here. So there's something here that could be potentially interesting to look into, how we can use and if we can use it, and we would love suggestions from you audience. Thank you.